This week's lecture is about diffraction. Now, diffraction is a funny business. When we talk about the light created by a combination of passing through two slits, we call that interference. But if we talk about the light created by a single slit, then the phenomenon that we're thinking about is called diffraction. Paradoxically, if we think about 3 or 4 or 5 or more slits, many slits, that's also called diffraction. So 1 slit is diffraction, 2 slits is interference, 3 or more slits also called diffraction. It's a little inconsistent, but it does make sense. Now, unlike the way the textbook does it, I'd like to start not with a single slit, but to start with many slits, 2 or more, and consider the pattern of light that you get from the phenomenon of interference acting among 2 or 3 or 4 slits. Let's start out by talking about 2 slits. We have light from a source of a particular wavelength lambda passing through 2 slits. The 2 slits are separated by a distance d, and then they shine onto a distant screen, so the light from each slit goes through a distance r1 or r2 to reach p. Now, the key thing for the 2-slit interference pattern, you'll recall, is the difference in these distances. In fact, the phase difference for the 2 waves that arrive at this point from the 2 slits, that phase difference phi, is equal to 2 pi times the difference in these 2 distances, let's call it r2 minus r1, divided by the wavelength. It's the difference in terms of number of wavelengths times 2 pi. That's the phase difference. And you'll have constructive interference when this phase difference is something like 0 or 2 pi or 4 pi or so on. You'll have destructive interference where this phase difference is pi or 3 pi or so on. And of course, if this screen is far away compared to the distance between the 2 slits, there's a simpler way of writing this. This distance is R2 minus R1 is d times the sine of the angle between the horizontal direction of this diagram and the direction of point P, and so we could write that the phase difference is equal to 2 pi times d sine of theta over lambda. And this phase difference will lead to constructive or destructive interference in the 2-slit pattern. So let's see how that works by actually drawing the phasor diagram illustrating this phase difference. Okay, so we're looking at the phasor diagram of the 2-slit experiment. And because there are 2 slits, there are 2 little phase arrows. And they're in the same direction at the middle of the diagram there, where the distances are equal. But the total wave has a phase arrow, which is the sum of these 2 arrows. So that's the yellow arrow in our diagram. Let's start at the middle and move outward from the center. As we move outward, there comes to be a phase difference between the 2 slits, which will be an angle between the 2 blue arrows. And so as that changes, the yellow arrow changes direction and gets shorter. And of course, the square of the length of the yellow arrow is the intensity. We show the intensity of the pattern on the right-hand side of our diagram. And so that gives rise to that familiar sinusoidal variation in the intensity that we saw last week. So what happens if we have 3 slits? Well, if we have 3 slits, that produces 3 contributions to the overall wave that arrives at point P on the screen. And they'll come along 3 different distances, so there will be 3 phase arrows in our phasor diagram. The total arrow will be the sum of those 3, and the phase angle between the phasor for slit 1 and slit 2, or between slit 2 and slit 3, that angle between the phasors, the phase difference, will be in phi 2 pi d sine theta over lambda, where d is the distance between adjacent slits. Let's see how that works out. In the center of the pattern, we have 3 arrows all in the same direction. But as we move from the center of the pattern, there becomes a phase difference between adjacent slits, and that arrow gets smaller, and then longer again, and smaller and longer again. And notice that that there are 2 minima between each major maximum, each pair of major maxima, and also there are some secondary maxima where the slits don't add up to as much, the phasors don't add up to as much, but the intensity is as big as the intensity from one of the slits. So here's the intensity pattern for 3 slits. What do we see? Well, we have a set of intensity maxima. They're actually a bit narrower, not as wide as the intensity maxima for 2 slits, although as we'll see, they're spaced apart in exactly the same way. And between these intensity maxima, it's a little bit more complicated. There are, in fact, 2 intensity minima and 1 secondary maximum of intensity between each primary maximum pair. So where are those primary maxima? Well, they occur when all of the phase arrows line up. That is to say, when the angle between them is 2 pi times some integer. So from this, we can see, that since this is the phase angle between adjacent slits, we can see that the condition is just the same as the condition that we had before. D sine theta is m times lambda, where m can be 0 or 1 or 2 and so on. The locations of the maxima for the 3-slit pattern are just the same as the locations of the maxima for a 2-slit pattern with the same slit separation. But in between the maxima, things are more complicated. So where are those intensity minima? Where are the places where you have destructive interference among the 3 slits? Well, that'll occur when the 3 phase arrows exactly add up to 0, when they form a closed pattern like this. And the first place that'll happen is where this angle, the angle between the first arrow and the second arrow, is 2 pi over 3, 1/3 of a complete circle. That'll form a closed triangle. So at 2 pi over 3 for the phase angle, that means that d times the sine of theta, which is the difference in distance between adjacent slits, d sine theta, will equal lambda over 3. 1/3 of a wavelength between adjacent slits. Then the slits will contribute to add up to the same thing. But you'll also have destructive interference if it's not lambda over 3, but it is 2 lambda over 3. It'll just make the triangle, but in a slightly different way. So either lambda over 3 or 2 lambda over 3. Either way, the phase arrows will make a complete triangle, and we'll have destructive interference. An intensity minimum for 3 slits. How about 4 slits? Well, for 4 slits it works like this. In the middle of the screen, all 4 phasor arrows add up to one big arrow. And as we move to the side, the phasor arrows curl around, and they form minima and secondary maxima before they finally add up and form another maximum. And so the pattern that you get has primary maxima. In between each pair of primary maxima, there are 2 secondary maxima and 3 intensity minima. The pattern for 5 slits works just the same way, except between the primary maxima we have 3 secondary maxima and 4 intensity minima, where there's destructive interference among the 5 slits. So where do those intensity minima occur for 5 slits separated by D? Well, for perfect destructive interference among the 5 slits, the phasor arrows will have to go like this. They'll have to form a closed pentagon. And the angle between adjacent ones will be 2 pi divided by 5. And so that means, using our formula for the phase difference between adjacent slits, that d sine theta will be lambda over 5. But of course, it'll also work out that they'll add up to 0 if that angle is 2 times lambda over 5, or 3 times lambda over 5, or 4 times lambda over 5. These conditions give you the locations of the 4 intensity minima between each of the primary maxima in the 5-slit pattern. So for the intensity pattern for 5 slits, we have primary maxima wherever d sine theta is equal to an integer times the wavelength. So the primary maxima occur where that integer is 0 or 1 or 2 or minus 1 or minus 2. That's where you have the primary maxima. In between each pair of primary maxima, you have 3 secondary maxima and 4 minima. Those minima occur where the d sine theta is lambda over 5, or 2 lambda over 5, or 3 lambda over 5, or 4 lambda over 5, to look at the ones between the 0th and 1st order primary maxima. Maybe you're noticing a pattern. When we have just 2 slits, the maxima are located at where d sine theta is equal to m times lambda, where m is an integer. And there are no secondary maxima in between, and only one minimum of intensity in between each pair of maxima. And that's located right in between lambda over 2. But suppose we have 3 slits, the maxima occur at the same place as before. But there's a secondary maximum in between the 2 primary maxima, and 2 minima located lambda over 3 and 2 lambda over 3, where the phasors add up to 0. When we had 5 slits, the maxima were located in the same place, but there were 3 secondary maxima in between each pair of primary maxima, 4 minima located lambda over 5, 2 lambda over 5, 3 lambda over 5, and 4 lambda over 5. So in fact, that's a general pattern. If we have, let's suppose we have n slits, some number I don't know. Well, the primary maxima will occur at exactly the same place, although those maxima will be narrower the larger n is. How many secondary maxima are there between each 2 of these primary maxima? Well, there are n minus 2 of those, and n minus 2 of those, and n minus 1 minima in between. Where are those minima? Well, they occur at lambda over n and 2 lambda over n, all the way up to n minus 1 times lambda over n. There are n minus 1 of them in between. N minus 1 times lambda over n. And that's what the pattern for n slits will look like. Just for fun, let's look at the phase diagram for 8 slits. There are 8 little phase arrows, and as we move from the middle, those phase arrows add up in various ways, producing a pattern where we have primary maxima located just where we had them before, but in between each pair of primary maxima there are 6 secondary maxima and 7 minima. If we have a great many slits, hundreds or thousands of slits, then we have what's called a diffraction grating. The number of slits is very much bigger than 1. Very, very large. And the situation for a diffraction grating is very easy to analyze. The maxima, the intensity maxima, will be at the familiar places where d, the separation of the slits, times the sine of theta, theta being the angle, is n times lambda, where n is just some integer, positive or negative. But those maxima are now very, very narrow. They're just very well-defined directions. And the secondary maxima that lie in between these primary maxima are very numerous, but they're also extremely faint. So they're so faint that they are, as a practical matter, invisible. And all we see are the very well-defined primary maxima at these directions. Now, one of the useful things about a diffraction grating is that we can use it as a way of separating wavelengths from a source of light. In fact, it's much better than a prism, which relies on the dispersion of the index of refraction to different wavelengths. It works like this: if you have a diffraction grating, then light coming from this direction with some particular wavelength lambda 1 will get diffracted in a few directions. Here's one of them. It'll also go straight through. Here's lambda 1 at an angle theta 1. But if we have light of a different wavelength, lambda 2, say a longer wavelength, it will get diffracted at a different angle, theta 2. Lambda 2, where the connection between angle and wavelength is simply given by this relation for the location of the intensity maximum. So diffraction gratings are really useful, and in practice, that's how we, in the laboratory, split up light into its constituent wavelengths with diffraction gratings. Having thought about the diffraction pattern that arises from many slits, let's turn our attention back to one slit. It turns out one slit is a lot more like many slits than it is like two slits. So that's called single slit diffraction. So we have a light source. Light is impinging on an opaque barrier with a single opening in it of a certain width. Let's call that width W. And Huygens principle leads us to suspect that the light is going to spread out in all directions. Instead of just having a beam of light that's exactly the same width as the slit, we expect the light to spread out on the downstream side of the slit. But how does that happen exactly? How do we analyze what's going on? Well, the trick is to regard this single slit as being composed of a large number of smaller slits right next to each other. So here's how it works. We have one slit with an opaque barrier with one opening in it, and that opening is of width W. So what we're going to do is we're going to imagine that that single slit of width W is a whole bunch of slits right next to each other. They're not separated by anything. They're just in fact touching each other. But each slit only is 1 over n, if they're n slits, times the entire width, and they're separated by W over n. So the light that comes from the whole slit is actually produced by light coming from each part of the slit. And all of this light will interfere. It'll produce a multiple slit pattern. So the idea is we're going to divide the single slit into n slits, conceptually. The separation of adjacent slits, d, is W divided by n. And in the end, we're going to consider that number n to go to infinity. Okay, let's begin the analysis. Remember, the separation of our imaginary slits is the width of the single slit divided by n. And let's think about where the primary maxima of the pattern of those slits might be. Well, of course, we have an equation for that. D times the sine of the angle is an integer times the wavelength. And that integer could be 0 or plus or minus 1 or plus or minus 2 and so on. So we can solve that for the angle. The sine of theta is equal to this, but we've also substituted the fact that this d is just W over n. So we get m times lambda over W times capital N, which is the number of slits. But we're going to imagine that that number of slits is immense. We're going to treat that single slit as composed of an immense number of tiny slits right next to each other. So as that number goes to infinity, the right-hand side gets much larger than 1. There's no solution unless m, the order of the maximum, is equal to 0. Then the right-hand side stays equal to 0. So the only solution for a large number of slits will be theta equal to 0. The only primary maximum that we will see in our pattern is the one in the middle, the central maximum of the pattern. There won't appear any other primary maxima. There might be secondary maxima and minima, but no primary maxima. So we sort of know what the pattern is going to look like. There'll be a central maximum of intensity, and then there will be some secondary maxima on either side with minima in between. And we also remember that the separation of our imaginary slits is just W divided by N. So let's try to locate the minima of this pattern. This is the central part of a pattern for a very large number of slits. Where are these minima? Well, we know from our previous analysis that d sine theta is going to be some integer m times lambda over n, where m could be 1 or 2 or 3 or 4, and all the way up to n minus 1. So this is the location of those minima. By the way, these are the locations of the minima to the right of that central maximum. The ones to the left will be located in pretty much the same kind of place, except we'll take m to be negative. So m could be plus or minus 1, plus or minus 2, and so on. But m is not 0. Where m is equal to 0, we have the central maximum. So d is w divided by n. So we have w over n sine theta is m lambda over n. We can multiply both sides by the number of slits, and we have an equation for the locations of the minimum. W, the width of the slit, of the overall slit, times the sine of theta, is m times lambda, where m is plus or minus 1, plus or minus 2, and so on. That's the location of the minimum. Now that equation has a kind of familiar look to it. So whenever you have more than one equation that looks the same but means something different, it's good to sort of review in your mind how they are different, what's different about them. The first equation we saw is d sine theta equals m lambda. And that's an equation that applies when you have 2 or more slits. The quantity d here is the separation of the 2 slits, the separation between their centers. And this equation tells us the location, the angular location theta, of the intensity maxima from the interference of all those slits. And finally, m is an integer, which can be 0 or plus or minus 1 or plus or minus 2, any integer at all. Each integer will give you a maximum for the intensity pattern for multiple slits. On the other hand, the equation we've just arrived at is w sine theta is m lambda. In this case, it's an equation that applies when you have a single slit. And w here is the width of that slit from side to side. And this equation gives you not intensity maxima, but the location of the intensity minima, the location of the dark spots in the pattern. And m, the integer that occurs in this equation, can be plus or minus 1, plus or minus 2, and so on, but not 0. Any integer except 0. At 0, you'd have theta equal to 0, and that's the location of a primary maximum, the only primary maximum, in the single slit pattern. So, 2 equations, they look kind of the same, but they mean very different things. Just for fun, let's look at the phasor diagram for a single slit. Well, imagine that the slit is divided into a whole bunch of slits, so the big phasor arrow is the sum of a whole bunch of tiny arrows in the middle of the pattern. They all point in the same direction. But as we move out from the middle of the pattern, we see that this set of arrows curls around into a curve and produces first a minimum, and then a smaller maximum, and a minimum, and a smaller maximum, and a minimum, and even smaller maximum, and so on. As you go out from the middle, it winds around, it gets smaller and smaller. Even the maxima are shorter and shorter. And that's how the pattern builds up. And in the end, you wind up with a single slit pattern that looks something like this. So here's what the single slit intensity pattern looks like. And there are a couple of things to note. First of all, notice that that central maximum is twice as wide as any of the others. And it's also a lot higher. In fact, it's more than 20 times as high as any of the other intensity maxima. So to first order, you can suppose that essentially all of the light is in that central maximum, but the light is spread out over that central maximum. Then there are a few other bright spots a little farther out. So how wide is that? So the light through the slit goes in one direction, and then it's at an angle delta theta on either side of that central peak. Delta theta. And we'll suppose delta theta is pretty small. Of course, that angle is just the angle of the first intensity minimum from the single slit pattern. And if we assume that the angle is small, then the sine of theta is about equal to the angle theta, in this case delta theta. So that means if m is equal to 1 and delta theta is about equal to sine of delta theta, that means that delta theta, the half width of this pattern, is about equal to the ratio of the wavelength of the light to the width of the slit. And that has the following kind of nice consequence. It means that if you change the width of the slit, you'll change the width of the pattern. If you make the slit narrower, the pattern will in fact get wider because that delta theta goes as the reciprocal of the width. So a narrower slit means a wider diffraction pattern. The light is spread out over a wider angle after it passes through the slit. We can illustrate this with a rather silly demonstration. This door amounts to a slit through which waves may propagate. Now, you notice that when I'm standing by the door and I go to one side of the door, you can no longer see me, but you can still hear me. Why? What's the difference between sound waves and light waves? And the answer is kind of strange. The answer is that light waves are very short wavelength waves. Very, very short. Less than a millionth of a meter. And so the spreading out of the light as it passes through this very wide slit, tens of centimeters wide, the spreading out is almost nothing. So light passing through a wide aperture like this door spreads out almost not at all. It almost goes in straight lines, and so you can't see me around the corner. The light can't be bent around by the presence of this slit. But sound waves are much longer. The sound waves of my voice are on the order of a meter in length, and that's actually even longer than the width of this slit. So the sound waves passing through the door spread out, and the door can cause those sound waves to bend quite a lot. So the reason that you can hear me but not see me from around the edge of the door is that sound waves and light waves pass through the door, but sound waves are very much longer in wavelength than light waves. Okay, so that's the initial lecture on diffraction. We'll talk a lot more about things in class on Monday for a while, and a lot more on Wednesday. So I'll see you in class.